Several different types of trucks are used to transport the hot mix from the plant to the paving site. Probably the most common is the tandem dump truck, carrying approximately 15 tons. Depending on the size of the project, length of haul, and the scope of the work, other types of hauling units may be used. Using the proper number of trucks is a key factor in providing a steady flow of material to the paver. Regardless of the type of hauling unit, it is important that the truck is kept in good, safe operating condition, clean, and properly outfitted for protecting the mix from contamination. A truckload of hot mix is worth several $100s, so the payload is worth taking care of. The National Asphalt Pavement Association publishes a booklet called Truck Driving Techniques. It provides a good review of proper techniques for everyone who is part of the asphalt paving team. We recommend it to you. With a properly prepared foundation on which to place the hot mix, skilled workmen using good equipment will construct strong, durable asphalt pavement. These pavements will serve for many years and will be a credit to those who build them. It is recommended that a tack coat be applied prior to placing each pavement course. Recommendations for the type and amount can be obtained from Institute engineers or in pertinent Institute literature. When constructing successive asphalt courses with little or no delay, there may be instances when a tack coat need not be applied. In order for paving equipment to do the job it's designed for, it is mandatory that everyone who has a responsibility for placing the hot mix understand the principles behind the design and operating characteristics of the paver. The tractor unit supplies all of the power needs of the paver: motive power to drive it, hydraulic pressure to operate rams and hydraulic motors, and electrical energy for instrumentation and control. The screed unit is towed by the tractor unit. It consists of a screed plate, vibrators or tamping bars, thickness controls, crown control, and screed heaters. Let's take a look at some of the main features of the two basic components of the paver. First, the tractor unit. Whether rubber tire mounted or track mounted depends on the preferences of the manufacturers, the preferences of the contractor, and to some extent, the kinds of projects the machine is generally used on. The speed of all pavers can be varied over quite a wide range. This allows the paver to maintain steady forward progress consistent with the rate of delivery of the hot mix. Good practice calls for continuous operation with few, if any, stops by the paver. Frequent stops and starts produce rough pavement. Many pavers are equipped with hopper wings that fold in for easy cleaning and to prevent accumulation of segregated mix or chunks of cold material. Slat conveyors transport the hot mix from the receiving hopper back through the body of the tractor unit. Adjustable flow control gates regulate the amount of material transported to the screed. Screw augers then distribute the material laterally so that a controlled amount of material is kept in front of the screed all the time. It's well to keep in mind that the tractor unit is simply a mover. It's the power source for the machine, and it moves the hot mix to the screed unit for proper spreading. All pavers operate on basically the same principle as to leveling and control of thickness of spreading. As the screed is pulled into the material, it automatically seeks the level at which all forces acting on it are in balance. This slide illustrates the forces acting on the screed. The basic action of the full-floating, self-leveling screed may be compared to a water skier who is pulled along the water surface with her skis tipped up just enough to support her weight. When the screed is tipped up with respect to the direction of the tow arm pull, the uplift offered by the mix flowing under the screed is increased. The screed will rise until W and V are in balance, and then level off, leaving an increased mat thickness. On the other hand, when the bottom of the screed is tipped down with respect to the tow arm pull, the amount of uplift is reduced. The weight of the screed forces it down until the angle of attack becomes parallel to the direction of pull. At this point, W and V are again in balance, and the screed levels off at the reduced mat thickness. The screed is continually attempting to bring or keep all of the forces in balance. The bottom of the screed must be smooth and true to lay the mix properly. In addition to normal wear, two other causes of screed problems are: 1. The leading edge of the screed is not properly crowned, causing uneven wear across its width, and 2. Overheating, which may warp the screed. In addition to striking off the mix at the proper elevation and maintaining the correct thickness of mat, the vibrating screed consolidates the mix and imparts initial compaction. The amount of compaction developed by the screed varies with the properties of the particular mix being laid. The screed usually consolidates the mix to about 80% of its target density. Rather than vibration of the entire screed, some paver models employ what is known as a tamper bar. This bar slides up and down at the leading edge of the screed to compact the mix just enough so the screed can follow smoothly over the tamped mix. The tamper bar should extend 1/64 of an inch below the screed at the bottom of the stroke. Crown adjustment is important for proper texture behind the paver. Both the leading and trailing edges can be crowned or changed proportionately. The leading edge of the screed should always have slightly more crown than the trailing edge. But too much crown in the leading edge of the screed will produce an open texture in the mat along the edges. Too little crown in the leading edge will cause open texture down the center. The screed assembly also is equipped with fan-augmented heaters. Heating the screed prevents the mix from sticking to the screed plate. It is used to heat the screed plate at the start of paving operations or to make up for lost heat on a cool, windy day. Heaters should never be used to attempt to add heat to the mix being delivered to the paver. A properly adjusted asphalt paver that is in good operating condition is capable of laying a smooth pavement. But there are some basic operating guidelines which have to be followed as well. Good pavements just don't happen accidentally. They're built that way on purpose. Probably first and foremost is to keep the paver moving at a constant speed. At every location where the paver stops, the screed leaves its imprint in the surface of the road. When forward motion is resumed after a prolonged stop, the screed rides up on the cooler material which was in the auger area or boot of the paver. This causes a slight thickening of the mat for a short distance and a resulting bump in the pavement. Since it's a simple matter to calculate the paver speed needed to match plant output, there's no reason to start and stop and start and stop. This slide shows curves from which paver speeds can be determined. For example, if a hot mix plant producing 250 tons per hour is supplying a paver laying a mat 3 inches thick and 12 feet wide, the paver speed must be 20 feet per minute to balance the laydown rate on the road with production at the plant. In addition to stopping and starting the paver, certain other poor practices will also cause waves, texture problems, and rough pavement. One of these is failure to deliver a constant supply of mix to the spreading augers. Too little mix ahead of the screed will cause it to settle. Too much mix ahead of the screed will cause it to climb. This slide summarizes the effect of auger loading on mat thickness. It's also important to keep the distribution of material in the augers as even as possible. Properly adjusted, most paving machines will automatically keep a steady supply of material in front of the screed. Another factor which can cause variation in mat smoothness and surface texture, and perhaps more serious deficiencies with sensitive mixes, is failure to hold the forward speed of the paver constant. When the paver moves more slowly and the tamps or vibrations are closer together, mat density increases and the screed will tend to rise. However, if the forward speed of the paver increases, the tamps or vibrations are spaced farther apart. Then, mat density decreases, and the screed will tend to drop. It is simply not possible to obtain a mat of uniform density and satisfactory smoothness unless the forward speed of the paver is held constant. Remember then, keep paver starts and stops to the absolute minimum. Keep the auger loaded correctly, with enough hot mix to maintain a level about at the midpoint of the auger diameter. Maintain an even distribution of hot mix in front of the screed. And keep the speed of the paver constant. Most large asphalt paving projects now specify that electronic grade-controlled pavers be used. This equipment makes it possible to keep all layers more uniform in thickness, thus providing a smoother pavement. By means of the grade control system, the angle of attack of the screed can be varied to an up or down attitude. Grade is controlled by a sensor, which takes signals from an erected string line or wire. For example, if the paver enters a hollow in the road, the grade sensor detects the fact that the tow tractor has dropped and signals for the mat to be thickened. The sensor readings are transmitted to the hydraulic controller of the tow point ram. By raising the tow points, the angle of the screed is altered to bring about the necessary change in mat thickness. Pavement cross slope is controlled by the movement of the tow point ram on the side of the paver opposite the grade sensor side. A pendulum mounted on a beam senses the difference in elevation between the beam ends. This cross-slope controller signals the tow point ram so that the screed may be maintained at the desired cross-slope. Thus, it is seen that one side of the screed is controlled by the grade sensor and the opposite side by the cross-slope pendulum. This slide illustrates the various parts of one type of automatic grade control system. Starting at lower left, the principal parts of the automatic grade control system are depicted. The sensor transmits readings taken from the string line. These signals are transmitted to the grade sensor hydraulic ram, which raises or lowers the leveling arm toe point as needed to change the angle of the screed. The pavement cross slope is regulated by the cross slope controller. This controller senses changes in the slope of the transverse beam and activates the hydraulic ram on the opposite toe point. In addition to making it possible to lay asphalt pavements to a precise grade, automatic screed controls have greatly simplified the incorporation of superelevation into curves, where the superelevation is to be accomplished with the asphalt courses. About 50 feet ahead of the point of curvature, the operator begins dialing out any cross slope that was being maintained and enters the curve with the screed horizontal. The curve itself is divided into 4 equal sections. The curved transition section is divided into 8 or more equal increments for dialing in the superelevation in 0.5% changes until the full amount of superelevation has been introduced. The center 2 sections are the portion of the curve where the full amount of specified superelevation is in the screed and remains unchanged. The ending section of the curve, like the beginning, is divided into 8 or more equal increments for dialing out the superelevation in 0.5% changes. In the next 50 feet or so, the specified cross slope is dialed back in. Wood laths make good station stakes, since they are tall enough to be seen by the operator, and the percent of cross slope to be dialed in or out can be marked on them. When increasing the superelevation of curves with manually controlled pavers, the standard practice has been to place successive wedges, which are thicker on the outside edge than on the inside edge. Successive lifts are placed until the required amount of superelevation has been developed. To eliminate the need for co-longitudinal joints, 2 or more pavers may be used to place full-width pavements on large projects. But on many jobs, only 1 paver can be justified, making a longitudinal joint necessary. While some harsh mixes are more difficult to joint than others, proper care and correct techniques will ensure a durable, maintenance-free joint. The amount of overlap should not exceed 2 inches. There are 2 commonly used methods of constructing longitudinal joints. In one, the overlapped mix is crowded back into a bulked ridge of uniform size so that the breakdown roller can press this small excess into the hot side of the joint. On a crowded joint, care should be taken not to broadcast any excess aggregate over the surface of the unrolled mat. A trimmed longitudinal joint is sometimes used. This is constructed by removing all of the freshly lapped material. When this method is used, the trimmings are usually carried forward and put back in the hopper. In the compaction process, the longitudinal joint is compacted first. 2 principal methods of constructing transverse joints are commonly used. Shown is the bulkhead method at the end of the day's run. When ready to start paving again, the bulkhead and supporting hot mix ramp are removed. Another widely used method of constructing transverse joints is to place building paper or roofing felt under the joint. At startup, the ramp and the portion of the mat over the building paper are removed. Regardless of the method used to construct the transverse joint, it must be carefully checked with a straight edge. If it is not true and smooth, the full thickness of the mat should be removed far enough back to correct the situation. After initial compaction, the joint should again be checked with a straight edge. Any deficiencies should be corrected immediately. A transverse joint should not be left until it is right. Good equipment will perform the tasks for which it is designed only when properly cared for. Thorough cleaning of the paver at the end of the day is essential. All manufacturers provide owner's manuals which show lubrication points and intervals. These specifications should be followed. Cleaning the machine also affords an opportunity to check for needed adjustments and repairs. On many paving projects, the safe and courteous directing of traffic through the work area is a major part of the job. Traffic control devices and procedures should be well planned and be appropriate for the volume and speed of traffic using the facility. The traffic control measures employed should also be designed to allow for efficient and safe movement of construction equipment, hot mix trucks, rollers, inspectors' pickups, and other authorized construction traffic. Hazards must be adequately identified and marked or barricaded. Flag persons should be properly trained and outfitted. Pilot cars may be necessary. If used, they should be properly marked with visible signage. All procedures should be designed to keep everyone on the job safety conscious, alert, and aware of potential dangers. This slide presentation has been designed to acquaint you with the basics of asphalt hot mix paving equipment and technique. The equipment shown is not endorsed by the Asphalt Institute or the National Asphalt Pavement Association. The scenes were chosen to demonstrate certain points we believe are important. The techniques demonstrated may not be the only ways to accomplish the tasks described, but they do represent good practice. Viewing this presentation will not make you an expert on asphalt paving. We do hope, however, that it will help you understand some of the basic operations common to most asphalt paving projects. We thank you for your attention.
Any quick questions or comments?
I saw a Newford sitting in a median. Or on one of the slides, like a Newford gauge was sitting in a median.
Yep. Yeah, that didn't look too good.
Campbell or something, I don't know what kind of gauge it was.
And on the end there, they showed some traffic control devices and procedures and techniques that are obviously out of date and so on. But as I said earlier, the paver operates today pretty much just like it did years and years ago. Keeping everything consistent about the operation is the key to a good, smooth, dense paver. It talks about a lot of the things that you saw in the slide presentation here for the next several pages. In the manual here, I would suggest that when you get a chance, read through this. That puts us over to page about 9-33 in the manual before we get into compaction. Boss will be talking about that in just a second. But before he does get started, I would ask you to quickly turn to page 9-48, I believe it is. This is where in the manual it gets into talking about construction of joints, those transverse joints and longitudinal joints. And in those sections there, 9.9 and 9.10, the very first paragraphs there are exactly from the standard specifications. And then it talks about the construction procedures for constructing joints. There have been some recent changes in recommended practices on constructing longitudinal joints. These are for the most part detailed here in the manual. If you're going to be involved in a construction project, I would ask you to read through those. Constructing joints is very, very important. Even constructing them exactly like the recommended practice is, it's going to be a relatively weak area in the pavement. And so you want to construct those joints correctly such that they won't separate. They'll be relatively smooth for years to come and so on. Constructing joints is pretty important in constructing a quality asphalt pavement. Any questions? If not, with that, I'll turn it over to Paul.
I know you're not going to like to hear this, you need to back up to page 933. We're going back. Jim mentioned this section deals with compaction. First, I want to ask the question, what is compaction? Consolidating material. When you do consolidate those aggregate particles in asphalt binder, what are you doing? You're actually reducing the number of air void spaces within that mat. If you have too many air void spaces in that mat, they tend to become interconnected, which allows the intrusion of air and water. What does both air and water have in it? Oxygen. When oxygen comes in contact with that binder, what's it going to do? It's going to oxidize it and make it become brittle. Jim told you this morning that this is a flexible pavement. If that traffic load goes across it, it's sitting there flexible. If that binder becomes brittle and oxidized, what's going to happen? It's going to start cracking. The more traffic that goes across it, the more it's going to crack, and then eventually it's going to open up and start popping out, and you wind up with a pothole. Compaction is considered successful when you achieve the minimum density requirement set forth in the specification. On all super pad mixes, what is the minimum compaction? 92% of the maximum specific gravity, or what we refer to as GMM. If you look in your manual, it goes on to say except. There are two exceptions there. You have the SF 9.5A, which is 90% of that maximum specific gravity, and you have the S 475A, which is 85% of that maximum specific gravity. But all other super pad mixes, no matter what traffic level it is, A, B, C, D, will be 92% of that maximum specific gravity. We're going to take a look at a little video now that lasts about 5 minutes. It follows along pretty much with our manual. It deals with equipment, rolling procedures, and things like that. We'll take a look at it, and then we'll come back and we'll come through the manual and discuss some of the items that we saw in the video.
Presses the mix and reduces its volume. This increases the HMA density by increasing the amount of mix in a given space. The roller's job is to compact the mat to a specified density. Proper compaction increases a mat's durability and strength. It reduces rutting, moisture damage, and low temperature cracking. The number of coverage coverages a roller needs to achieve a required density depends upon a number of factors. These are mix composition, including the types of aggregate and asphalt cement commonly used, mat thickness, uniformity, aggregate size, and mix temperature at time of rolling. Compaction is also affected by the temperature of the base and the air, wind speed, radiant solar energy, and speed of the roller. For all projects, the time available for compaction needs to be established and may change over the course of the day. The better understanding you have of the compaction process, the better your pavement is going to perform. Rollers are impressive pieces of equipment and often work close to passing traffic. Safe roller operation at all times is essential. The various types of rollers used for compacting an HMA mix are selected according to the conditions and needs of the paving operation. Three basic types of rollers are currently used: the static steel wheel roller, the rubber-tired or pneumatic roller, and the vibratory roller. Static steel wheel rollers are used for breakdown, intermediate rolling, and finish rolling. Rubber-tired rollers are typically used for intermediate rolling, but can also be used for initial and finish. The number of tires varies. For effective compaction, each tire should be the same size, have the same ply, and the same pressure, as this determines its compacting effectiveness. Vibratory rollers vary in their type, size, and number of drums. Vibratory rollers compact the mat by combining the force of its weight and that delivered by an adjustable impact force produced by a rotating weight inside a drum. Both frequency and amplitude can be adjusted. They are typically more efficient than static rollers, but must be used carefully. Determining which type of roller to use depends on a number of variables, including type of mix, thickness, rolling patterns, and the desired density level. Critical roller components that should be kept in good working order at all times include the water spray system, hydraulic system, mechanical system, drums, and tires. Keeping your equipment in top working order and controlling compaction variables is essential to keeping your project on schedule. The level of density achieved during the compaction process can be affected by several factors. When the following factors are known and understood, they can be controlled. Roller speed. Increasing speed decreases compaction per pass. Ideal speed depends on paver productivity, layer thickness, and roller position. Number of coverages. The minimum number of coverages to achieve required density depends on roller position in the train. Rolling zone. Required density must be reached before the layer cools too much to be compacted. The rolling zone is the area of the mat that is at the right temperature to be compacted most efficiently. Rolling pattern. A good pattern results from the most efficient and effective combination of all the compaction equipment used to achieve target density. Because compaction requirements depend on existing conditions, a test strip is built to determine roller types and patterns needed to reach target density. The strip, usually about 300 feet long, is actually part of the job and should be placed and compacted in the same manner as the job is scheduled to be. Rollers to be used are determined by their availability, the mix production rate, and the width and depth of the mat. The number of coverages needed to reach target density depends on the roller types, their speed, and position. All of these factors determine the rolling pattern. The distance between the roller and the paver should be as short as possible to densify the mix while it is easiest to compact. A nuclear density gauge is often used to measure the compaction effort after each pass until reaching target density. Once a rolling pattern is established, stick to it. Keep the rollers moving. Throughout breakdown, intermediate, and finish rolling, the rollers should maintain constant speed, making as few stops as possible. Care should be taken to ensure that transverse and longitudinal joints are rolled correctly. It's important to remember that test strip activities establish the rolling pattern and operating techniques for the scheduled taping.
As I said, it's a short video, but it had a lot of good information in it. You'd go on over to page 934. On this page, it lists some of the requirements and specifications pertaining to the rolling equipment. Let's see, it's about about the fourth paragraph down. It says you're going to compact all wearing surfaces, final wearing surfaces, use of a minimum of 2 tandem steel wheel rollers. You've got to have at least 2 steel wheel rollers. It goes on to say that if you're using a vibratory roller, which is specifically designed for compaction asphalt pavement, you can use it on all pavement layers that are 1 inch or greater in thickness. It goes on to tell you down there that the engineer may prohibit the use of a vibratory roller that has a likelihood of damage to the mat you're replacing, underlying pavement structures, drainage structures, utilities, and things like that. There are actually some divisions that do not allow the use of vibratory rollers due to a lot of damage being done to the underlying subgrades, especially down the eastern part of the state where the water table is real high. Over on the next page, it gets into the type of rollers it talked about in the video. You see there's the steel wheel roller, pneumatic tire, rubber tire roller, and a vibratory roller. If you go on through the next couple of pages, you can see we have a little write-up there. Under steel wheel rollers, we've got one there, the 3-wheel roller. I doubt any of you here has ever seen a 3-wheel roller. I don't know if anybody's even got one anymore. I probably all gone to the recycling bin or something. But they were, in their day, a good piece of equipment. Probably still would be a good piece of equipment, especially doing widening. Where these 4, 5, 6 foot wide drums now, if you're only doing 3 foot wide, it won't get down in that trench and a bridge on that existing pavement. Those back wheels are 18, 24 inches wide. You can actually put it down in that trench and get compaction on your widening. And then you go on, it talks about the tandem rollers, then it gets into your pneumatic tire rollers and vibratory rollers. Point out to you the vibratory rollers, there's 3 very important factors that has to be adhered to for it to work properly. You've got your frequency, amplitude, speed. You got to get all 3 of those coordinated correctly, or you're going to wind up with a washboard ride in your pavement. Going on through, it gets into your compaction procedures. I'm not really going to go through that. On 939, the last paragraph, it tells you there, you see a bolded underlined statement. What does it say? Fuel oil shall not be used. A lot of contractors like, especially on their rubber tire rollers, put fuel oil on the rubber tire to keep it from sticking. Actually, what you're doing when you put fuel oil on it is damaging the asphalt layer that you're trying to compact. Because that fuel oil comes in contact with that binder, it will actually strip it off from the aggregate. So they did not allow the use of fuel oil. Overall, about halfway down 941, you see there, it lists factors that affect compaction. There are 5 things listed there. You got your mixed properties. You can actually go into the lab and design a mix that's practically oxygen conditions. Then it talks about your environmental conditions, air temperature, road surface temperature, wind, things like that. Your layer thickness. If it's too thick, it's difficult. If it's too thin, it's hard to compact. Subgraded bases. You've got to have a good subgraded base to make sure you get good compaction on the asphalt material. And of course, always make sure your equipment's in good working condition. Under all of those things there, it's not listed as one of the 5, but it's listed under mixed properties. If you read on through, is your mixed temperature. Mixed temperature is one of the most important factors in being able to get compaction. The hotter that binder is when you start compacting, the easier it is for those aggregate particles to slip around one another. Once it starts chilling off, that binder gets stiff and it's harder to get compaction. So you need to get your roll on as hot as you can without damaging it. And the next couple of pages just talk about what we just talked about there. 945, our third of the way down, you see 3 phases of rolling. You got your breakdown on intermediate, breakdown on initial phase of rolling. This is where you use the steel wheel, tandem roller, or a vibratory roller. This is the phase of rolling which you get on most of your compaction. Once you finish that breakdown phase, you should have at least minimum compaction. Because the mix is starting to cool off enough now that it's going to be very difficult to get any more compaction out of it. The next phase is your intermediate phase. Normally people use a rubber tire roller for that. It's still warm enough to get a little bit of compaction. If you only get 90, 91, you're not going to get 1.5% out of it. You may be able to get 2 or 3 tenths, maybe 0.5% compaction from your intermediate phase. And of course, you got your finished phase of rolling. This is the purpose of the finished phase of rolling. Get out roller marks. The other 2 rollers left in the mat, you want to use that to get those roller marks out. The optimal number of passes for a finished roller is 1. Because that mix is starting to get cool enough, and if he's just sitting out there rolling back and forth just to have something to do, what's he going to start doing? He's going to start breaking back what density you do have. So if he catches up, doesn't have anything to do, just back up on the cold mat back there and just sit and wait until he can go. And that gets us up to the page 948, which is where Jim left off with the joint. Anybody have any questions? Not? Give us one.
Turn over to page 10-12 in your manual. Very briefly, we're going to cover the requirements for pavement smoothness. One of the things that you check the pavement for after it's been placed and compacted is to be sure that it rises smoother as well as our specs require. We have 2 different methods of checking pavement smoothness or rideability here in North Carolina. And very quickly I'm going to touch on both of those. Basically just sort of tell you what they are. We're not going to go into a lot of detail here on either one of them. If you look there at 2 or 3 sentences down into the first paragraph under final surface testing, it mentions 2 methods of surface testing are utilized by the NCDOT. The first method it mentions is one that's required out of our standard specification book. You'll see that it says Article 610-12 of the specifications requires that at any location on the pavement selected by the department and all joints be checked using a 10-foot non-mobile straight edge. 610 in the specifications is on final surface testing and pavement smoothness, and in there it requires the contractor to furnish a 10-foot, we say non-mobile there, it's talking about a stationary straight edge. As you'll see in a few minutes, the other method we use utilizes the 10-foot mobile straight edge. So we're just trying to distinguish between the two. The requirement in the spec book is that the contractor furnish a 10-foot stationary straight edge. It goes on to say in the specs that that straight edge is to be used by both the contractor and the department to check pavement smoothness, or the spec requirements. It then states that if you place that 10-foot stationary straight edge longitudinally, that means with the flow of traffic parallel to the center line on the pavement, that there should be no more than 1/8 of an inch deviation between any 2 contact points. So that becomes your spec requirement. 10-foot stationary straight edge, longitudinally on the pavement, no more than 1/8 of an inch deviation between any 2 contact points. As I say, that's in our standard spec book. It has been in there as a requirement for as long as any of us have been working with the state. It's a very basic approach to checking pavement smoothness, but it will in fact find rough pavement. The other method is in the form of a project special provision. What did we say this morning that the special provision was? Change the spec book. I just told you what's in the spec book. In the spec book, it requires a 10-foot stationary straight edge. That's what you would utilize unless you happen to have this project special provision in your contract. If you look there in the middle of that page where the heading is Final Surface Testing - Asphalt Pavements, and then the July 18th, 06 date out to the right, beginning there, all the way over to the top of page 1015. You'll notice that print's a little smaller, a little different than the other print in the manual. That is the project special provision. We simply copied it into the manual. It happened to copy a little differently, and we just left it that way so you can tell that. That is the provision that you would see in the contract. This provision is used in selected contracts. If you go back up this paragraph above that heading, it says in selected contracts, the final surface testing using a 10-foot rolling profilograph. This is in fact a profilograph. It does plot the profile of the pavement on a piece of paper. So it's technically a profilograph. We commonly call it a straight edge, but it is a profilograph. If this provision is in the contractor is required to purchase and furnish the 10-foot rolling straight edge, do the testing with the straight edge. The straight edge is this is in the first sentence under the provision itself. The straight edge is the North Carolina Hearn straight edge model number 1. That's at the end of that first sentence there. Tells you that he is required to use the North Carolina Hearn straight edge model number 1. We do require that contractor purchase that straight edge from a manufacturer that we have a contract with, so that everybody uses the same piece of equipment. And it is referred to as the North Carolina Hearn straight edge. For any of you that may not be familiar with it, this is the straight edge, the 10-foot rolling straight edge. As you're looking to it, the front's to your left. This is the front. 10 foot long. The operator normally stands here. This is the push bar or guide bar, and he simply holds on to and he walks along and pushes the device at a normal walking speed over the pavement. As he's pushing it along, the center wheel is the recording wheel here. The chain device that you see coming up is connected down the bottom, and it comes up to the top where it's connected to a marking pin that's marking on a adding machine tape that's being rolled through there, fed through. As you push it along, it marks the profile of the pavement. Here's a shot of someone pushing along, normal walking speed, and as he's pushing along, it's marking the profile of the pavement. This is a shot from up top just to give you an idea of what it sort of looks like. This is the profile that it's plotting. The line you see going there is the profile that it's plotting. There's a blanking band that's laying in there. This band here is a blanking band that's used to sort of evaluate the tape, that it plots the profile there. In our introductory class, we don't get much deeper into the spec besides just to show you that and tell you that there are two different methods of checking pavement smoothness. In the roadway technician class, we get into a lot of detail on the special provisions requiring the roll and straight edge. We go through the entire provision and cover it in great detail, even to the point where we evaluate the graphs and stuff in there to show you how to do that. But for our purposes here, just realize that there are two methods. One is the stationary straight edge, as required by the standard specs, unless you have a contract that has this provision in it, and then the contract is required to use the rolling straight edge. Any questions?
Now we can move forward. Go to section 10. We are in section 10. Let's skip on over. Page 1025. This section deals with your density testing, methods of density testing. As you can see there's two possible ways to check compaction on a product. Nuclear gauge, or samples taken directly from the compacted pavement, core samples. I don't care which one the contractor uses, it's up to him. Contractor or his representative at the pre-construction conference will tell the engineer which method he's going to use. Whether he says, Mr. Resident, I'm going to use nuclear control of this product. So that's what he's going to use. If he chooses nuclear, he's got to use that through the duration of that contract. He can't do nuclear today, coal tomorrow, nuclear the next day, so on. Whichever method he chooses, he has to use it throughout that entire contract. Any questions on that? On the top of page 1026, table 10.2, we discussed those earlier. These are the minimum density requirements, which is 92% for all super paved mixes, with those two exceptions, S945A and S475A. All other super paved mixes are 92% of the maximum specific gravity. The next section that tells you how we determine acceptability, and it's done on a lot-by-lot basis. A lot, in most cases, will be considered 1 day's production of a given mix type on a given contract. And that's going to be, like I say, in most cases. There are some other circumstances that might occur that will cause you to have more than one lot in 1 day's production. And they're listed there. There's several different items listed there that what they may be. Over on page 1029, first paragraph there, the testing frequencies, it tells you there that you're going to have one test station for every 2,000 linear feet or fraction thereof. A test section will be 2,000 linear feet, or at the end of the day, if you only have 1,500 feet, that last test section would be 1,500. It goes on to tell you what you're going to test. Of course, you're going to do all your full width travel lanes and Y lines and stuff like that, and there's several other things there that we won't go through in this class. On page 1030, you see a minimum sampling schedule. Wayne went over one with you for mix at the plant. We have something similar here for density control, one for core sample control and one for nuclear control. Just to give you an idea of whether you're getting the right number of samples at the right location. Let's see. Over on the next page, it gets into placing and obtaining core samples. It used to be that we could use a piece of paper as a separator medium. Everybody's probably familiar with this now. I think it was in 2005 we went away from using a separator medium. Now you have to just place it, cut the core. If you have to go all the way down through the entire layer of paper structure, and you have to do that to separate the layer to be tested. But we do not allow separated medium. Samples will be taken no later than the beginning of the next day's production, not to exceed 3 calendar days. 3 calendar days doesn't mean that I can wait 3 days to cut those samples. It's 3 days is there to take care of the weekend. If I pay on Friday, I can wait till Monday to cut my core sample. If I pay on Friday and pay again on Monday, then I have to cut those core samples Saturday morning. Once you have obtained that core sample, it tells you there that it's going to be cleaned, dried, lightly or properly coated with tack, and then a mix of the same type placed in there, and that must be done within 1 working day. That is a slight change. It used to say immediately, but we found out that statewide that there was 1,000 different definitions of immediate. So we put within 1 working day in, so everybody would do the same day, that same thing. Over on page 1032, Wayne discussed the random sampling procedures for mix. We do the same thing for density testing, and this goes into procedure at this point here. We use the same process, ASTM B 3665, alternative 2. Start in the left-hand corner, go down that column 0. Let's see. As you notice, these random numbers have 4 digits. Mix only had 3. The reason for these having 4 is the first 2 digits are used to determine the longitudinal location. The second 2 digits are used to determine transverse location. The intersection point of those 2 random numbers is where that density test site will be located, whether it be nuclear or core. There are 10 pages of this table. Each page is not a separate table. All 10 pages are table 10-4. Okay, page 1043, we get into nuclear gauge procedures. Contractor, if he uses nuclear control, he requires to have a certified gauge operator. That certification is handled through materials and test soils unit. They have a class, you take a test, and then they will come out and actually watch you perform tests in the field before you're fully certified. With nuclear control, you're required to do a control strip at the beginning of production of each mix type on each contract. Provided that original control strip is a good, or what we refer to as a good or passing control strip, it will be good for plus or minus 21 calendar days, at which time the contractors will be required to place another control strip. And if you read on down through that, it will give you several other instances in which another control strip would be required. Again, on page 1049, talks about test sections, plot 4 test sections, equal 2,000 linear feet of fraction thereof. And that gets us over to page 1055, which is nuclear gauge quality assurance. It's done by the department or department representative. Basically the same thing that Wayne went over with you. There's 5 different things listed there, and I'm not going to go through those now due to lack of time. Over on page 1060, we get into core sample control, quality control core sample. Unlike nuclear gauge, you are not required to have a control strip at the beginning of production on the process. The only time that during core control that you're required to do a control strip is if you have to go to limited production due to failing density. Or if you look down there, if the engineer requested you to do it, then you would have to do one. You do not have to do one at the beginning of construction. Over on page 1064, it gets into determining the random locations for core samples. We've got an example there that is spelled out with numbers and everything in there. I'm not going to go through that. Just let you know that these numbers are kept and recorded on Form QC5 by the contractor, either a certified nuclear gauge operator or certified roadway technician will fill this out. This is just the form, the summary form of that. So if you get a chance sometime between now and the time you go to the roadway class, you may want to look at it because we go into that in detail in the roadway class. On page 1072, we go into quality assurance core sample. Again, the 5 items listed there, and I'm not going to go through those either. We do both verification and quality assurance cores with 5% for quality assurance and 10% for verification core. Over on page 1077, mentioned limited production a minute ago. Contractor responsibility to keep up with his density records. If he is required to go to limited production, he has to place himself. The department is not required to say, hey, Mr. Contractor, you've got to go to limited production. It's his responsibility to do that. 3 things listed there that would require a contractor to go to limited production. The first one says there's 2 consecutive failing lots except on resurfacing contract. If I'm out here, I cleared away, built the subgrade and everything on up, what I call construction, then you have 2 consecutive failing lots, which in most cases is going to be 2 days. You have to go into production. And if you're on an actual resurfacing contract, where you're replacing a layer on top of an existing pavement, then you have 3 consecutive failing lots you have to go in and conduct. If you're using nuclear control, then you have 2 consecutive failing control strips to go to limit conduct. Any questions? That takes care of that for me. Any questions at all about density testing and reporting and stuff? If not, let's turn on over to page 11, or section 11. This section deals with records and reports. I think Jim mentioned to you this morning that it's very important that you keep accurate records and reports. We, at times, have to go back and look at these reports, especially if we have failures. We'll go back and look at these reports, and if they're not accurate, we can't determine anything. If we can look at these reports that are accurate, we may be able to determine what the problem is, or what the problem was. We won't be able to fix that problem, but we can help prevent it from happening in the future. So make sure we get good, extensive, accurate records. Over on page 11.2, the first section there, talking about records and reports. Bolded underlined statement there just says there'll be no erasures, whiteouts, or any other means used to correct errors that are made on any QMS form or worksheet. If you do make an error on one of those worksheets or forms, and you cross through it with one single line, put the correct information directly above it, and put your initials there. But no erasing, no striking through, obliterating, stuff like that, one single line. Next section, retention of forms. Due to circumstances that happened several years ago, we have now required the contractor to maintain his forms for a period of 3 years. It was 90 days, and now it's 3 years. So the contractor has to maintain those forms for 3 years. How many in here from the department? I think only a couple, maybe 3. If you read on down through there, it'll tell you that we are required to maintain our QMS forms for how long? Indefinitely. So as far as I know, unless somebody's done something they shouldn't have, every form from day 1 of QMS we have at our QA lab. The next section, falsification of records. Jim talked about that this morning, so I'm not going to go into that other than to say, don't do it. On page 11-5, this is a summary sheet of all the forms used in the QMS process. And don't fall out in your seat when you look at them. Not everybody fills out every one of those every day. There's certain forms that are filled out by the contractors, some are filled out by the department, some are filled out for both. But you won't have to do all these every day. These particular forms are used in the QMS process. I would point out to you that down on the OJT checklist, QMS 3, QMS 5, they are probably the ones that you're going to be most need to be most familiar with at this time. If you haven't completed your OJT, then these are the forms that you would have to use. QMS 3 if you're going to the plant, and QMS 5 for the roadways. Over on page 11.6, this is where we start going through the rest of the manual is like this. It's all those forms we just saw in that summary sheet. This happens to be a plant form. It's the QA/QC1. It's used in the contractor's lab and the department's lab. If you'll notice, we have numbers in each one of the blanks. And then if you would go to the adjacent page, you see there's some instructions. If for some reason you're filling that form out and you get to a particular blank, you, and I don't understand exactly what they're looking for here, you can find that number, go over that number on the adjacent sheet, and then find out, to give you a little information on what we're looking for in that blank. Also, at the top, each form and the instructions will have a general note. This general note will give you certain information that may not be listed down through the instructions, especially on distribution. Some of our forms have distribution listed on the actual form itself, some do not. So you will find that in the general note. So make sure you read through that. And the rest of the manual is set up the exact same way, all the way through page 11-107. These are all the forms that are used. I think Wayne mentioned it this morning. Beyond that, beyond the appendix, there is an alphabetized index. So when you get ready to start your exam in a few minutes, if you get to something that's stumping you, instead of thumbing through the manual page by page, turn back to the index and help you find it a lot quicker. Any questions or comments? Okay, we're going to start the exam. I think Jim told us this morning, passing grade is 80. There's a total of 25 questions worth 4 points each. They're multiple choice, true, false, fill in the blanks. The cover sheet on the exam, make sure you read it. It's basically a statement on there saying that you have read what's on page 11-2, dealing with falsification of records, and if you understand what the consequences will be, you sign it. Put all the information it has to go on there. Once you have finished that, you turn over to the first sheet of the exam. You will have to repeat your name, last 4 digits of the Social Security number, and the date. Once you have finished your exam, back on the table that we're sitting at back there, you can just drop them off back there on the way out. As Jim told you this morning, it'll probably take you about 15-20 minutes is all it should take for this. If you have any questions, raise your hand and we'll try our best to help you.